Hello, everyone, and welcome to today's webinar, Leading the Industry in Direct Trace Elemental Analysis of Seawater with NexION ICP-MS. I am Marie Stone of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by PerkinElmer. To learn more, visit PerkinElmer.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. I'd like to now welcome our speaker, Kenneth Ong, Principal Inorganic Product Specialist, PerkinElmer, Singapore. Kenneth, you may now begin your presentation.
Good day, everyone. Before I begin, I would like to thank Dr. Eve Krabs, ICP-MS Product Manager, and Dr. Xing Li Yan, Senior Application Scientist of PerkinElmer, for allowing me to share their works with you. The materials was first presented on spectroscopy forums. Today, we will be talking about how our technologies can help to carry out direct trace elemental analysis of seawaters and to look at some of the works done by Dr. Singh. Now, about 71% of Earth's surface is water, and of this 71% of Earth's surface water, about 97% are covered by the oceans. You probably also know that entire populations obtain 25% of the proteins we consume from the oceans, and that is about $21 trillion in food supplies. The oceans, on top of providing us food, is where millions of people rely on fishing to make their livings. You may ask, with so many things like plastic, microplastic, organic pollutants, and other harmful things in our oceans, why would we be concerned with elements contaminants that are found naturally? With increased human activities, the rate at which these elemental contaminants being introduced to the environment has significantly increased. Source of these elemental pollutions must be identified so that we can reduce or eliminate their introductions into the oceans to create a safe living grounds to support the marine life. Elements introduced into the environments are non-biodegradable. They may change in their molecular form. They could become less toxic, but they can also become more toxic and more available for uptake by plants and marine life. As such, they are more persistent to remain in the environment for longer times compared to organic contaminants. There have been so many cases where the release of metals into the environment have led to disastrous consequences for both biomes and the ecosystems, such as deliberate or accidental release of industrial pollutions or the spillage during an accident on the sea. While most countries follow WHO in monitoring the coastal waters, some have their heavy metals monitoring programs and regulation specifications for enforcement. Two examples of these programs are the Malaysian's Marine Waters Quality Standards and the Australians and New Zealand's Environment and Conservation Council Water Guidelines. There are a few challenges that need to be addressed in the analysis of seawaters. Seawater samples are known to have high total dissolved solids, and if you have lots of samples for testing, you would like to be able to reduce downtimes and routine maintenance in order to maximize your productivities. The complex natures of the seawater samples present another challenge. The techniques that we use to correct for this polyatomic interference from the plasma gas and the major components of the seawater's matrix will affect the accuracies of our result, and this must be addressed. Now, the longer you analyze the seawater, you are going to get more salt into your systems, and that could choke up your orifice and cause signal drift. As important as speed of analysis, you would also want to have longer stability despite the complexness of the matrix. So you did like to have some features that will help to improve and ensure long-term stability. We will be discussing on how we address these challenges and needs. ICP-MS has long been the instruments of choice for trace elemental analysis. There are different types of ICP-MS, such as the simple quadrupole ICP-MS without a cell to correct for polyatomic interference. So you really have to rely on inter-elements corrections to get the right result. Or you can have a single quartz analyzer with the cell to remove polyatomic interference through either collisions or the reactions. We can also have or use a triple quartz instruments which are able to filter analytes before they enter the cell. And finally, there are multi-quadrupole ICP-MS that has the capability beyond triple quartz systems of having active controls over the reactions in the cell, as well as an additional quadrupole before the first analyzer quadrupole that replaces conventional lens systems, and we'll look into that a bit more in the details later. To show the difference of a quadrupole systems versus a multi-quadrupole systems, we'll look at NexION's platform as an example. Both the NexIONs have an additional quadrupole Q0. The benefits of this design is that it allows ions to be diffracted at 90 degrees into the downstream optics, while the neutral species and the photons will continue on straight path into vacuums without depositing on the surface with the help of a hyperskimmer cone. There are no other lenses in the designs that will require frequent cleaning. As such, NexIONs practically require no cleanings beyond the cones. This is very important for heavy matrix samples analysis, such as seawater applications. The Q0 can apply with a fixed or a scanning voltage in synchronized with the quadrupole. With a fixed voltage, you can create a mass filtering only masses within 16 atomic mass units of the targeted mass will be allowed to pass through into downstream optics. Again, these mass range trimming capabilities provide additional advantage in complex matrix analysis. If you compare the optics beyond the Q0, you will see that in the case of the NexIONs 1000 and 2000, there is a missing of Q1 before the cell, where there is a Q1 in a triple quartz or NexIONs 5000 multi-quadrupole ICP-MS. The Q1 not only acts as an additional filters, it allows mass shifting operations to be carried out in a more precise manner. What may not be obvious to you is Q2. The quadrupole in the cell is capable of rejecting high amounts of low masses with respect to the targeted mass, so that when reactions cluster products form, the chances of interference at higher masses are greatly reduced. This feature is especially useful for those quadrupole systems which don't have an additional Q1 before the cell. To illustrate the differences between triple quadrupole ICP-MS and multi-quadrupole systems, we'll look at what is happening inside a conventional triple quartz in the next slide. A conventional triple quadrupole ICP-MS have two stages of mass resolutions on Q1 and Q3. In these systems, there is typically a lens system which is used to focus the ion beams. From there, the ion beams pass through to the first transmissions analyzer quadrupole for the first stage of mass resolution. In the MS-MS on mass or the mass shift mode, only mass of interest is allowed to proceed and transmit into the cell. All other ions at different masses are rejected by Q1. In this example here, mass 52 are transmitted through Q1, while other masses such as argon-40 and carbon-12 ions are rejected. When mass 52 enter the cell, the ions are subjected to reactions for the best interference removal. So in this case, argon carbons with mass 52 reach the cell and start reacting with the ammonia, the cell gas that we commonly use. They either transfer the charge to ammonia or dissociate into argon and carbon ions. Although the ions in the cells are well characterized, the cell with higher order of multiple rods, such as hexapoles or octopoles, are passive cells. Its only function is to act as an ion guide to transmit ion through the cells and therefore offer no mass resolution functionality. To understand why this is so important in the above examples of pure ammonia gas that was added to the cells to remove argon-carbon interference from chromiums at mass 52, as I explained earlier, unfortunately, additional interference can form from the reaction's byproducts. In this case, the reactive ammonia gas form cluster at mass 52, which will not be separated in the cells or the subsequent Q3 analyzer quadrupole. In this product scan mode analysis, where we have intentionally turned off the active bandpass in the cell, even when Q1 only allows ion of mass 52 to enter the cell, the ammonia was introduced to the cell directly, you could see new classical ions were forming at mass 18, 19, 35, and 52. This produced around 5,000 counts at mass 52 as observed, which is a combined signal of chromium purities in methanols, the samples that we analyzed, and ammonia cluster, which leads to false positive in a result in a passive cell. In the multi-quadrupole ICP-MS, as in the case of NexION 5000, there are 4 stages of active resolutions. 2 additional stages of mass resolutions are the quadrupole before the Q1, which is the Q0. It replaced the traditional lens systems. The other additional resolutions, which is not obvious to most people, however, is of paramount importance, is in the Q2, which is the active reaction cell. The quadrupole ion diffractors, besides turning the ions 90 degrees into the downstream optics, it also trims down the ions with masses that are different from the targeted analyte mass and totally eliminates uncharged ions. Back to the Q1 filters, as with the traditional triple quadrupole system, it allows only the mass of interest to proceed to the cell, while all other ions are rejected. However, the real difference comes in with an active quadrupole cell. In the NexIONs, we call this the universal cell with dynamic bandpass tuning. The cell is a true quadrupole cell and it provides an additional stage of mass resolutions and actively destabilizes and rejects reactions byproducts before they have a chance to react with gas or gas impurities, thereby prevents false count at targeted mass of interest. In the NexION's ICP-MS with the capability of setting dynamic bandpass functionality in the cell, we can see that all previous observed peak from ammonia and the gas cluster at mass 18s and 35s are removed, leaving a clean analyzed signal at mass 52, which is around 500 counts per second, and that is corresponding to the real chromium impurity in the samples. This is a comparison of a product scan mode in NexION 5000. The pictures on the top is a scan where we have turned the bandpass tuning in the universal cell off, and we're looking for vanadiums in an ultra pure sort. You can see that we are picking up about 100 counts of false vanadiums. In the pictures on the bottom, we have turned on the bandpass settings, just as with earlier slide. Cluster at lower mass around 35 were rejected by Q2. The cell actively prevents byproducts from forming, and we are seeing a much lower count at mass 51. This is so important for trace metals determinations of seawater. Only ICP-MS with bandpass will give you a true detection of chromiums and vanadiums at lower levels, where having a Q1 in front of an passive cell isn't enough. So to speak, the performance of NexION 1000 or the 2000s with ammonia reaction mode in vanadiums and chromium determinations at mass 51 and 52 is much more superior than an ICP-MS triple quad system with a passive cell. Now that we know how to take care of polyatomic interference, let's move back a step and look at how we can handle the high dissolved salt contents in seawater. Analysis of seawaters can add a great deal to any lab in terms of the time it takes to perform it and the increased cost of consumables. The high salt contents not only increase the maintenance needs, it results in plasma loading effects and may suppress the ionizations of analytes with high ionization potential such as mercury, arsenic, and selenium. We could do this with an all-matrix solutions EMS systems in the NexION, which is a simple aerosol dilutions capable up to 200 times dilutions. Now, maybe a lot of you are not aware, we have this capability of adding dilutions gas since the Iran's era. The AMS not only just simplified sample preparations, with the salt contents reduced, we could reduce depositions on the interface and also effect a more efficient ionizations, thereby generating higher quality data for elements such as arsenic, selenium, and mercury. However, it should be noted that the gas dilutions is universally applies to all elements, and lights and measures metrics are alike. For coastal water analysis, we may not only be interested in trace toxic elements, but are also interested in major elements. Since the NexION cell is a true quadrupole cell, it can effect a selective attenuation. The dynamic range of the detector is increased to more than 12 orders of magnitude without causing damage to the detectors and impacts on their usage life. The selective attenuations or the extended dynamic range can be extremely useful for coastal waters and is unique to quadrupole-based cell, analyzing both high and low concentrations of analytes within a single analysis run. Using the AMS and the EDR or extended dynamic range together offer great deals of flexibility in analysis of seawaters. You can see in this image, we have a scan of 100 ppm of sodium and magnesium. The blue signals is without any dilutions. Signals are saturated for both sodium and magnesium. For the same solutions, we can effect an aerosol dilutions using the AMS. With this, the thickness of sodiums and magnesiums are reduced as shown by the red lines, since AMS effects a universal dilution. For the green signals, we have applied EDR selectively on sodiums and on top of using the AMS. As you can see, the signals at Mars 23 decrease, but since the EDR was not applied to magnesium at Mars 24, its signals remains unaffected just as with the red lines. So with the combinations of gas solutions and the quadrupole cell, you have the flexibility of analyzing measures and trace analytes in seawaters within the same methods. Dilution is not the only way we can reduce the depositions on the cones. If we can keep the samples loading as short as possible, as it is required only during analysis, we will be able to prolong the intervals for the needs to clean the cones. One way of achieving this is by means of a flow injection technique. Not only does it help to shorten the exposures of cones to salt build up, it can enhance the sample's throughput. As you can see from the two samples uptakes and analysis time chart on the left, the red signals is with a conventional auto-samplers loadings. The total exposures times of the cones to the salt loadings from uptakes to washdown could be as long as 7 to 8 minutes. Whereas with a flow injections such as the high throughput systems or the HTS from PerkinElmer, we could potentially cut the exposures times to a short of 2 minutes with the same length of times needed for analysis by ICP-MS. If you look at the signal charge on the top right, the samples draw up quickly by means of a vacuum into the plasma in as short as 9 seconds. From the points the probes move into the samples, the signals is stable in the plasma much faster, and potentially we could start the ICP-MS analysis after about 12 seconds from probe downs into the sample vials. What the HTS does is it reduces the residence times of the samples in the plasma. The AMS also allows for online dilutions of internal standards on top of reducing maintenance frequency and dramatically reduce samples runtimes, hence improve samples throughput. The NexION's instrument supports the PerkinElmer's high throughput systems or HTS, as well as all full range of ESI fast systems and CTEX express system. Now that we have an idea of tackling the biggest challenges in analyzing seawaters, we are ready to do some actual analysis. Now, seawaters has a salinity of around 3 to 5%, and it contains small amounts of other inorganics and organic materials. So let's recap. There are two main aspects of seawater samples that makes analysis with ICP-MS challenging. Firstly, seawaters contains high amounts of sodium, chloride, magnesium, calcium, sulfates, etc., and will have interference on ICP-MS analysis. Secondly, the trace elements that we are analyzing, the heavy metals, can be of very low concentrations. Now, the high dissolved salts will have matrix effects, which leads to severe signal suppressions or enhancements, and of course, long-term stability signals instability due to salt and carbon deposit on interface. It definitely will have spectra or polyatomic interference generated by the plasma-based ions like argons, carbons, and oxygens with the salt, which will overlap with targeted analytes. For example, argon chloride and calcium chloride on arsenics, argon with a sodium at mass 63, that will be copper, and argon with magnesiums on zinc at mass 64, and chlorine with the oxygens on mass 51, and of course argon with the carbons on chromiums. Now, the concentrations of trace elements are in a range of ppb down to ppt levels. Now, as mentioned, the NexION platforms are equipped with universal cell technologies, and the NexIONs can operate in standard mode without the use of any cell gas, in collisions or KD modes using neutral gases such as helium, and reactions mode with dynamic bandpass tuning using a variety of reactive gases. Now, with the NexION 5000 multi-quadrupole ICP-MS, there are two basic processes, MS-MS and mass shift mode, to achieve interference-free analysis. With the on-mass MS-MS mode, analyzed ions and interfering ions with the same mass are selected by Q1. Once enter Q2, the interference start reacts with the cell gas and are rejected, and the analyzed ions are analyzed in Q3. Example of such modes of analysis is in the determinations of chromiums, where calcium carbons or the argon carbons are removed. Now, in the mass shift modes operations, the interference remains unreacted while the analyzed ions react with the cell gas in Q2 to form higher mass ions. The Q3 will scan at higher mass where the analytes has moved to, while the interference are rejected. Example of such mode of analysis is in the determinations of arsenic 75 in the presence of argon chloride, where arsenic ions react with oxygen cell gas to form arsenic oxide at mass 91. There are a few approaches in seawater sample preparations for ICP-MS analysis. First approach is a simple offline dilution, and we can perform manually or using standalone automated equipment, while it requires additional costs for dedicated equipment. It is still laborious and will have high risk of contaminating the samples. One step advanced will be using an inline dilution, such as the use of PrepFast from ESI. Of course, this adds on additional costs. The next approach is with sample pre-concentrations using a columns to remove the matrix components while retaining the pre-concentrated analytes of interest, which will be backwashed by a buffer solution into the ICP-MS for analysis. This can be done manually or with the elegant equipment like the CFAS. The advantage of this approach is obvious. However, it adds on additional costs to instruments investment. It is not an easy approach as you need to really take care of the columns, preparing the buffer that must be metal-free, and it lengthens the sample-to-sample analysis time with loading, pre-concentrating, and backwashing step. Now, our approach will be using a regular samples introduction systems with no manual dilutions nor expensive accessory. It combines the liquid dilutions with the internal standards and aerosols through the all matrix systems. Not only does this approach do away with expensive accessory, there are no additional labor steps, no steep learning curve on new samples handling accessory, and most importantly, reduce the possibility of contaminating the samples during handling. We apply a two-fold gas dilutions by all matrix solutions and a five-fold liquid dilutions through the internal standards. The EMS argon gas is introduced to the next of the spray chambers where it meets with the primary aerosols, thus reducing the amount of analytes into the plasma, which practically dilutes the samples. The liquid dilution is achieved by using a larger ID pump tubing for the internal standard solutions introductions, while a smaller IDs for the samples to effect a 1:5 dilutions on the samples. To reduce the samples loads to the plasma, high throughput system is used and it delivers the samples to the plasma only during the data acquisition stage and diverts the samples to the waste for the rest of the run. By means of a vacuum, it draws and diverts the samples to the samples loop in a very short time and perform wash procedures more efficiently and effectively than conventional peristaltic pump-based interaction system. Now, in this case, the HTS is used in line with a S20 autosampler. We will be using the metric match approach, and that will be standard additions in the synergistic software. For the calibration standards were prepared in a 3% ultra clean sodium chloride from the ESI and acidified to 1% nitric acid. The mercury was calibrated in a low range of 0.01 to 10 ppb, and the rest of the elements were calibrated in a range of 0.1 to 100 ppb. 3 seawater CRMs were used for method validations where the NAS7 is originated from open sea waters, Class 6, and the MX014 are from coastal and the near shore waters. The certified values of these CRMs were shown on this slide. The NAS and CAR seawater CRMs are from the National Research Councils Canada. While there is no reference for selenium, it is still useful for method validations, and some elements such as zinc and ions are at such low levels would really need a clean environment to prevent cross-contaminations. The MX014 is a reference from the National Measurements Institute. It is actually a fortified seawater, and the elements are in a range of 1 to 5 ppb mostly. This range is more realistic to be achieved in most labs without a clean room environment. Listed in these tables are the instrument settings and parameters. We use a PFA microflow nebulizer as compared to a glass nebulizer. PFA has a slight advantage of low memories effects. The spray chambers come with an AMS matrix pot for us to effect the aerosol dilutions. The peristaltic pump tubings for the carrier was orange red with 0.19 mm ID, and the peristaltic pump tubings for the internal standards was orange yellow with 0.51 mm ID. The aerosol, or rather the AMS gas, was optimized for half the intensity of indiums in standards mode. 3 cell gases were used: oxygens, ammonias, and heliums. This table lists the masses, the mode of analysis for NexION 5000, and the gas profile used for each analyte. Just to use titaniums As an example, in the NexION 2000, we are using titanium at mass 48 using helium gas to remove potential polyatomic interference from SO and POH while using IEC corrections for calcium since helium does not remove the calcium. In the case of the NexION 5000, we have the advantage of mass shift mode, and that is what I meant by the mode of analysis. And yes, titanium was analyzed using ammonia cluster at mass 131, moving it away from the mass 48 interference such as the POH, SO, and calcium. Now, one important point that I want to highlight is the cone cleanliness. Now, a lot of times we want the cones to be as clean as possible for the start of sample analysis. However, for seawater applications, we would like to condition the cones. The cones will be well conditioned if we see a stabilized signals of internal standard elements, and this takes about 10 to 20 minutes of continuous aspirations of the seawaters or the 3% sodium chloride. Once the cones are conditioned, we can proceed to do the calibration. Shown here are some calibration curve on NexION 5000. On the top left here is the titanium measured with a mass shift ammonia cluster techniques. And on the right is the arsenics, again using mass shift with oxygens. Now vanadiums and the coppers are measured on the mass MS mode with ammonia bandpass settings for vanadiums to prevent side reactions as we discussed earlier. And since copper levels is typically not very low, we could do this easily in the collision mode. The accuracy was verified by the recovery of elements with the certified values in the seawater's CRMs. The recovery were within 10% for the analyte certified in open sea waters CRM NES 7 using the NexION 5000, and the recoveries were also within 10% were achieved for most analytes in the coastal seawaters CRM, the CAS 6 and the MX014 using the NexION 2000 ICPMS, and the arsenics and mercuries falling slightly beyond the 10%, but still within the 20% accuracy. Since there are few elements without certified values for the NES and CAS, a spike recovery test was used to validate the methods for those elements where seawaters was spiked with elemental standards and run as a samples. Now, a good recovery within 10% were obtained for all metric spike standards on the NexION 5000 system. Now, obtaining a good recovery is not enough. As with any environmental monitoring protocol, we need to ensure that the method has a detection limit capable of meeting or exceeding the specifications limits set by the regulatory bodies. All the method detection limits fulfills the detection requirements by the two seawaters monitoring programs mentioned before from the Australian, New Zealand, as well as the Malaysians. Those program specifications are in the green bars. In fact, method detection limits were in a single digit PPT to sub PPT levels for most elements. There are few elements that were at double digits levels, but they are commonly present in regular laboratories environments such as the aluminum, iron, nickel, copper, and zinc. Now, if you look at the orange bar, those are the detection limits for the 5000. They are much lower compared to the light purples that is from the NexION 2000. As important as accuracy and detection limits, long-term stability is a need and desirable for seawater's analysis. For this, the seawater samples were measured repeatedly over a period of 10 hours, and the CCV's recovery were monitored over this period to check for stability. As shown in this figure, there was no apparent trend throughout the run, demonstrating the validity of calibrations over the whole sample run, and all the CCV or continuous calibration verifications recovery were found to be within 20% of the original reading. This definitely will help high throughput laboratories in terms of overall efficiency and productivity by avoiding having to rerun the calibration standards, so that you spend more time doing your analysis rather than doing calibrations. Now I come to the conclusions of our discussions. A simple direct analysis of trace elements in seawater samples using NexION 2000 and 5000 ICP-MS can be carried out with the AMS and by means of an internal standard dilutions. The high throughput systems not only speed up the analysis throughputs, it reduces the exposures of cones from salt. The exceptional detections limits, accuracy, and long-term stability provide a strong evidence on the superior interference removal capability and the outstanding sensitivity of the NexION. Of course, comparing the NexION platforms, NexION 5000 has the advantage in sensitivity and interference removal capability. The results that Dr. Singh obtains prove that we are leading the industry in the direct trace elemental analysis of seawaters. With this, I thank you for your attention and have a smooth sailing in your seawater analysis.
Thank you, Kenneth, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen. We'll answer as many of your questions as we have time for. Let's get started. Our first question is, which type of ICP-MS is recommended for seawater analysis and why?
Hi, that's a very broad but a very good questions. Yeah, so the things about seawaters we have discussed is that it contains high dissolved solids. So you need ICP-MS that have the robustness to actually handle the matrices. Now the second thing is that a lot of ICP-MS are very concerned with drifting. So you must actually have a systems that are able to take care of salt build up such that it does not clog your orphy. So the NexIONs, as we mentioned, actually have a wide orphy. So that will actually helps to prevent the orphy from clogging up and causing signal drift. Now, of course, with that, we are going to get in a lot of salt into the ICP-MS, the ion optics. So then you must actually have ion optics that is capable of removing the uncharged particles as you get into the ion optic systems. Next is actually how we are going to remove the interference. So of course, I don't think anybody would want to do with a single quartz that is without a cell technologies. That is probably something that I do 30 years ago. So you probably want to go with a systems that come with a cell to help you to remove the interference. Otherwise, you really have to depend on mathematical formulas and you need to do a lot of predictions and assumptions. Now back to the reactions, so back to the cell. We can actually use reactions cell, we can actually use collision cell, and I think along the presentations we have discussed that. So for collision cell, we are going to use gases like helium. So there's no selectivity. It's actually based on the surface cross-sectional areas to remove the polyatomic interference. Now, if you go into a systems wherein the interference is as big as the analyte, then you're going to flow in high flow of heliums, and that will actually result in you getting very low sensitivity. So with the seawater analysis, as you see, we have to do some dilutions, and that is going to get your trace toxic elements to be very low levels. So the next best approach then is to use a reaction cell using ammonia gas, for example. That because of the selectivity is not going to reduce your thickness of analytes, and thereby allowing to achieve much lower detection capabilities. We also discuss on using a single quadrupole versus a multi-quadrupoles. I won't dwell too much. So we did mention that with the multi-quadrupole systems or the ICP-MS, MS, you have better control of reactions, and that certainly would actually be a added advantage of an ICP-MS using reaction cell. So I probably want to stop here. It's a very long questions to be asked, to be answered. So I will probably get in touch with these customers to actually discuss further.
Okay, thank you. Next question. I have an ICP-MS instrument from another company. Can I match the performance of NexION 2000 for seawater analysis?
Oh, yeah, depends on the types of the ICP-MS that you have. So if you are looking at just collision systems, I just mentioned that collision cell, if you were to analyze systems wherein your interference is as big as your analytes, then you need to actually flow a high collision gas, and that will actually result in you having a lower sensitivity. So definitely with the 2000s now, you have the choice of three gas channel. So you can still make use of the helium gas to analyze, for example, elements that is high in concentrations, that have fewer interference, because you do not need that kind of sensitivity. And for reactions mode, then you can actually make use of gases such as oxygens or ammonia gas to help you to remove the interference while actually retaining the sensitivity of your analytes. So certainly, I think with the 2000, it would in a way outperforms a systems that only provide just a collisions mode.
Thank you. Next question. For copper analysis, you have showed using helium mode. Do we have any advantage in using reaction mode?
Oh, yes, certainly. As I mentioned a while ago, so the copper's levels in the seawaters, especially in the near-shore seawater analysis, the levels are actually not low. So with that, of course, you can use helium modes to do your analysis. But when we are looking at offshore seawaters where the copper's levels that we want to actually check for are low levels, then the reaction modes will have the advantage, because now the interference of copper at 63 would be sodiums with argon, or it could be a sodium with a calcium that is in abundance. And if you look at copper 65, you will have interference coming from sulfur and phosphorus, which is also abundance in seawater analysis. So with that, we can use ammonia gas to actually help to remove the polyatomic interference. Now, we also discussed about 5000. Now, what we can do is that we can make use of, again, the ammonia gas. In this case, not for the ammonia gas to react the interference, but to get the ammonia gas in excess. So we'll flow a high flow of ammonia gas to react with copper and move it to copper 60, sorry, move it to copper, that will be 2 classical ammonia, and that will be at mass 97. So what we do is that Q1, or rather the first quadrupole, will focus in copper 63, and that certainly we are going to focus in your sodium and argon interference into the cell. And in the cell, we are going to now flow in high amounts of ammonia gas. Now, if you know about chemistry, high flow of ammonias, it tends to form cluster with a lot of metals. And that's what we are going to do. We are going to get coppers to form cluster with the ammonias and move it to mass 97. So Q3 will actually focus mass 97, which is the ammonia cluster. Whereas the sodiums and argons, they are not going to actually form cluster with ammonia. They are going to break off to sodiums and argons. And in that way, we are going to actually be able to detect copper at a much cleaner mass, and certainly would allows us to detect at a much lower levels. Okay, so that would be the advantage of using reaction modes. Thank you.
All right, thank you. Next question. You show that the aerosol dilute the sample 2 times and 5 times for the liquid. Can I just do a dilution with IS by changing the size of pump tubing?
So is dilutions with the internal standards? Well, certainly, yeah. So if you do not actually want to use the aerosols, the AMS systems to do dilutions, you can actually change the pump tubings depending on the size. So basically, a quick calculation would be getting the diameters, square of the diameters of your internal standards over the square of diameters of the pump tubings for the samples, and that will be the dilution factors that you will achieve through the use of internal standards to do your dilutions. Now, of course, you need to have a T-joint to actually join the two pump tubings out. Yeah.
All right, and we will wrap up with that question. Thank you, Kenneth. Do you have any final comments for our audience?
Well, yeah, so if you do want to know more information about the Seawater's analysis solutions that we provide, feel free to reach out to the sales representative in your countries, and we'll definitely get you more answers to your needs.
Thank you again, Kenneth, for your time today and your important research. We would also like to thank LabRoots and our sponsor, PerkinElmer, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, take care everyone and goodbye.